Last week we talked a lot about data I/O and dealing with EM data, converting to NumPy and that sort of thing. This week I thought we'd get a little bit more into some of the modular classes in EMAN2 and how it's useful to use those in many situations rather than switching to NumPy and that sort of thing. So the first thing I want to point out is this command e2help.py. So there are a bunch of these modular classes available in EMAN2 for doing different specific types of operations. I call them modular classes. If you were used to doing object-oriented programming, you might hear this referred to as a factory paradigm. There are different ways of talking about it, but the idea is, let's say you were using Relion and you wanted to add a new type of filter to the Relion post-processing. So you didn't like the top hat filter that Relion uses. You wanted to do something with a softer edge, like a hyperbolic tangent filter or something like that. What would you have to do? Well, you'd have to go into the Relion source code. You'd find the function where that post-processing is done somewhere in Relion, and then you'd have to add a bunch of new Fourier processing code in there to deal with the new type of filter, and then that filter would be available just in that one place for that one task and that sort of thing. So when we designed EMAN2, we wanted to combat that kind of problem, so we made things very modular. So there are different types of modular processing that you can do. One of the things, which would be sort of the situation I was just describing, would be just sort of generic image processing. To do generic image processing, you use a type of object called a processor. But then there are other sorts of things you might want to do. Let's say you want to, say you have a projection and you have a 2D image, and you need to have some similarity metric to measure how similar the projection is to the image. Well, to do that, first you'd have to align the two to make sure that they're in the same relative orientation. Once you had them aligned, then you would need to compare the similarity. So for those purposes, you've got aligners, which are used both in 2D and 3D to bring two objects which may not be in the correct orientation or position with respect to one another into alignment. And then that might be followed by a CMP, comparator, which is a similarity metric. So there are other types of these classes. There are averagers, which would be used for, as the name sounds, for averaging together. So if you have a bunch of particles which have all been aligned and you want to average them together, you could use averagers to do that. There are other types of averages for doing other types of operations, and we can look at that. Then there's projectors and reconstructors. These are the opposite sort of operation. Reconstructor will take 2D projections and produce a 3D reconstruction, or 1D projections and produce a 2D reconstruction. And projectors do the opposite. If you have a 3D volume, you can make a 2D projection of the 3D volume in a specific orientation, that sort of thing. Then there are analyzers, which sort of don't fit into the other categories. A processor basically will take an image as an input and produce an image as an output. An analyzer may take a bunch of different images as inputs and then produces some sort of analysis as a result. So those are the main modular types. There are some other things you can get out of E2help too, like a list of all the good box sizes. So if I say e2help.py, box size, you don't have to put the final S on if you don't want. And this will give you a list of all the good box sizes there are to use. If you use a number not on this list, then the image processing will run slower than it could have. And the list of good numbers here, these are basically just products of low prime numbers. So the numbers that are on this list as being good numbers are almost certainly also good numbers for Spider and Relion and any other cryo-EM image processing package that you want to do. These are numbers that work well with Fourier transforms. So this is a good list of numbers to use irrespective of the software you're using. Some of the other things, we may get into those later, the orient gens and the rotation types and the image types and that sort of thing. I guess rotation types we can talk about. EMAN supports various Euler angle conventions. So if you've got to reconstruct, if you have particle orientations that were done in the MRC convention in ReLion, and you need to convert those to EMAN's altitude azimuth phi convention, there's a class that allows you to do that. And then these are the different conventions that are supported. So EMAN, Imagic, MRC, quaternions, SGI rotations, etc. Okay, so not only will E2 help give you a list of the classes of the different types of objects that are available, it will also give you a list of the different members of each of those types. So we can say E2 help.py processors, and it'll give us a list of all of the standard image processing algorithms that are available in the system. And these are categorized. So, it starts with math dot or misc dot or test image dot. I've got picked some bad ones. There's filter dot, etc. So these are categories. Before the first dot, you have a category, and then after that is a subcategory, and possibly even a subcategory in some cases. So this will give you a list of all of them. If you want to search for one that does some particular sort of thing, like Eric was just asking me about thresholds, you'd say e2 help.py processor threshold, and that basically does sort of a grep through the list. It'll only pull out the processors which have the word threshold somewhere in their name. That corresponds to any part of the name, so threshold, so we could say binary. And that'll pull out a list of any processors which do something in a binary fashion. So you can see there are thresholds, but there are also morphological operations which are binary operations. So anyway, you can look through the list of processors this way with E2 help. And if you want more detailed help on something, so let's say I want to know more about the threshold binary processors, I can say -v2 or --verbose 2. I usually use V for obvious reasons. Oops. Sorry, I didn't say processor. And that'll give you detailed help. So now you can see threshold binary, and it'll tell you what each of the parameters means. So up here, there's a list of parameters for each of the processors. So here it'll say threshold.binary, f of x equals 0, if x is less than value equals 1, if x is greater than or equal to value. And then it has a definition of value. Oops. Sorry, I copied and pasted x accidentally there. And then anyway, it has a definition of value after that. So anyway, so this help system is available for all of the different modular classes. If I say e2 help.py cmp, it will give me a list of all of the similarity metrics. So there's a simple cross correlation similarity metric. You can use a Fourier ring correlation, Fourier shell correlation if it's 3D, and there's specific variants of that for tomographic data where there's a missing wedge, and it can take the missing wedge into account, or mean phase error, or a square Euclidean distance, or that sort of thing. So there are all of these different modular classes available. The nice thing about these classes being modular is that anywhere throughout EMAN you can make use of these modular classes. So if you're running a refinement in EMAN and you want to use a different type of mask than the default mask, you can specify which mask you wanted to use. And if you wanted to add a new image processing algorithm to the system, so let's say we say e2 help.py processor mask, and let's say, oh, I don't like any of the masks that I see here, I need to come up with my own mask. It's really easy to add a new mask to the system, and once it's in the system, you can just refer to it by name in any of the existing programs. You don't have to change any of the programs that use masking operations. You can just use them directly. All right, so let's talk a little bit about more about the image processing operations. So these sessions are supposed to be about Python. I'm going to start out with a command line program, which makes figuring out parameters and stuff easier. But then I'll switch to a more Python-based approach for situations where that isn't applicable. But we'll start out with this e2 filter tool.py, And then we need to give it some, you can give it stacks of 2D particles, individual 2D particles, 3D volumes. It takes all different types of objects. So I'm going to take SPT01, 3D0, let's see what we got, 404. I'm just going to give it a single 3D volume as input. And that'll open up two windows. It'll open up one window containing the 3D volume that I told it to read. And by default, it will open up with a surface rendering and a slice cut through the middle of the volume. That's just the default that it opens up. I can open the control panel as usual, and I can, for example, I can right-click there and I can turn off the slice if I don't want to see the slice, or if I want, I can add additional slices, you know, whatever. I can manipulate the display however I like. Now, what we have over on the left here is an image processing operation, which is one of those processors we saw with E2 help. So you can see it's categorical. So here we've got, or categorized. Here we can look at the classes. We can see, you know, there's filters, there's masks, there's thresholds, there's transforms. So there's all sorts of different types of operations. So if I wanted to do a filter, I would say filter, and then here I could pick from any of the various available filter classes. So you can see here are low pass filters, auto B factor, Gaussian, hyperbolic tangent, top hat. So I can do filters of various types. And once I pick one, then the parameters, it will show me here, each parameter will get turned into one of these value slider objects, where there's a slider associated with a text box, associated with a checkbox. And those will be specific to the particular operation, operation that I selected up here. So if I mouse over this, or actually mouse over this, it will give me basic help on the processor that I currently have selected. Now, the nice thing about this tool is once I've got these sliders and stuff, I can grab with the mouse here and I can adjust. Oops, sorry, I don't have it turned on. Let me turn it on. I'll explain that in a second. And I can adjust in more or less real time the level of filtration that I'm applying. So this gives you a nice interactive tool for adjusting things. Now, since I picked a 3D low pass filter on a fairly large volume, it takes a little while for it to update, but still it's there. There's actually an option you can give E2 filter tool at the command line, which adds a button you have to press to get it to do the update. So you can vary the sliders and then hit the button to get the update in case what you're doing is really slow. Now let's say I wanted to add another operation here. So this is just a filter. Let's say I wanted to add a threshold. Let's do a threshold. I hit plus here to add another object. And then I could say threshold binary. You can see there are a variety of different thresholds here. Binary threshold, which has a single value. If I look over here at my isosurface threshold that I'm using here, this is an isosurface threshold value of 3, or 3.33. So here, let's go ahead and set the value of that to 3.3. Now you'll note it isn't doing anything yet, and that's because I don't have this checkbox checked. As soon as I check the checkbox, now you can see the surface became really rough, and that's because it's pixelated, because it's a sharp threshold, right? So it basically, let me turn on the plane again, and you'll be able to see it clearly. All right, I'll turn on the plane, and then I'll raise the isosurface threshold a little bit. Yeah, it's not going to help a whole lot. All right, I'll turn off the isosurface. There we go. Now you can see the edges of what it looked like. If I turned off the threshold, you can see the density is actually varying in a continuous fashion. With the threshold turned on, you can see that it's a binary threshold, and if I change the value a little bit, I'll wind up including a larger or a smaller region. Even though it's only showing this in 2D, it's still doing it on the full 3D volume every time I change it. And since I have the low pass filter turned on here, it takes a little while to update. So if I turn off the filter, now I'm just seeing a threshold applied to the original object. And now if I grab the slider, it'll update a lot faster because the threshold doesn't take much time to compute. So you can put together these sequences of image filtration operations. You can adjust all the parameters. You can get everything like you want it. And then If you exit the program, you will find that there's now a file called filtertooldefault.txt. And if you read that file, you will see the image processing operation with the parameters that I had selected available in fashion which is compatible, in a fashion which is compatible with E2proc 2D or E2proc 3D. But these operations that we're looking at here, these image processing operations, can also be used from Python directly. Now, the filter tool is a great tool for building linear sequences of processors. But if you need to do more complicated operations, like say you need to merge image A with image B, but after doing some thresholding or something like that, or you need to do some translations or something like that, that's not something you can do in E2 filter tool. E2 filter tool is for taking a single, taking each image. I mean, you can give it a set of images to look at, but taking each image and doing a linear sequence of operations to that image, producing a single output. It doesn't have any way of merging data from multiple images or something like that. So if we wanted to do that, we have to switch back to Python again. So let me that. No, it only seems to open 2 windows now. Not sure why it does that. All right. Oh, and we've just got whatever session I last did when I was here. Oh, that's fine. There's nothing all that interesting here. Let me start from scratch. Okay. So let's take a look and see what files I've got here. Let's look for something 2D. Oh, that's not meant to do. Yeah, I don't know. I don't know if these classes are any good or not. Let's take a look and see what some of these look like, so we can pick some that are useful to look at. Okay, fine. So this is beta galactosidase. It's one of the test data sets. Like I'm having a font rendering issue on my Mac, but there should be numeric labels in the lower corner here, obviously, and they're coming up as black. Thought that bug had been fixed a long time ago. Apparently not. Anyway, so these class averages look okay. So yeah, we'll go ahead and play with that. So that's R2DB01 class is 00.hdf. All right, that's good. And maybe the and we'll read, I don't know, we'll read number 8. I don't know what it is. And maybe I'll start one of these display sessions talked about last time. Oops. Oh, it looks like I have my screen resolution issue again. Sorry, again, this is a Mac-specific problem related to using high-resolution display settings. very tricky to get it to actually do what you want it to do. 1920 by 1080. It doesn't have a low resolution version of that. Interesting. All right, well, we'll try, that's close enough. Let's try that. There we go. Okay, so now my image is getting displayed. Here's the actual image window it was displaying in. And now I can do stuff to A and we can display the results. So let's say A dot process, or we'll change it. We'll call it C is equal to A dot process filter dot low pass dot Gauss. Oh, let's do the threshold. Let's do the threshold operation. So let's say A of sigma 1.0. All right, so this is a normalized image most likely. So the mean is probably 0 and the standard deviation is probably 1. Or close to 0, not exactly 0. So I guess it's an edge normalized image, meaning the average around the edge of the image is probably 0 and the standard deviation was set to 1. So let's do a threshold at say 0.5. So we'll say C is equal to process, A dot process threshold dot binary, and then we give it a dictionary with the parameters. And in this case, so we can go back and do E2 help if we want. We could do it from Python as well, but I find this easier to do from the command line usually. Processor threshold, yeah, that's probably enough. Okay, so here binary threshold, and the parameter it takes is called value. So we just say value and 0.5. Okay, so now I have a new image C, which is A, having been thresholded. So we can do E3 display C image, and we'll call this test2 so we get it in a new window and we don't overwrite our original. And there we go. So there's our binary thresholded image. All right. Now, there are two operations you can use from Python to do this sort of generic image processing. There's process, and then there's process in place. So let me do this a little differently. We're going to make C a copy of A just so I don't overwrite it. And then we'll say C dot process in place. Okay, and that should do exactly what I did before. It made a copy of A into C, and then it applied the processor to C in place. In place meaning it overwrites the original image. So if we display this again, we should see exactly the same thing. If I change the value, we can see that it changed. Right? So a slightly different threshold. Maybe I should have made it even bigger. Hard to notice that it changed, but it changed. Right, so we can do various sorts of filters and other processors. We could do, say, a filter.lowpass.Gauss, and then the parameter that we need to use for that might be, say, cutoff frequency 0.1.
Sorry, can I interject here for a second?
Yes.
Because I was I'm trying to copy you as you go, because this is obviously exactly what I'm trying to do. And so as I was doing that, I think I missed what you were saying. The difference between process and process in place is they're the same. It's just process in place is going to overwrite. Is that what you were saying?
Process produces a new image, which is a copy of the image that image volume you're operating on, and process in place overwrites the image with the new processed image.
Okay, which is why you did a.copy and then it.
I did an A dot copy because I didn't want to lose A. Yeah.
That makes sense. Okay. Cool.
If I was going to do this, it would have made sense to just use A dot process instead of this.
Right.
Yeah.
Which is what you did first. Yeah.
Yeah. So if I do process in place and then I follow that with another process in place, and let's do the threshold.binary here and value 0.5. We have to display it again. Yeah. So now it did the filter, and then after the filter, it applied the threshold.
Gotcha.
Okay. Now, what about this cutoff frequency? So this is actually a point that's worth mentioning. So if we get help, okay, yeah, E2 help processor filter.lowpass, you'll notice, let me make this a little wider, maybe the font a little smaller, and then a little wider. There we go. So there are a bunch of parameters. You'll notice that a lot of these processors take a similar set of arguments. So there's cutoff ABS, cutoff frequency, cutoff pixels. And then there are some other options which are different for each one. So this is a standardization that we used specifically for low pass and high pass filters, which is there are different ways of specifying the cutoff frequency for the filter. It has a similar meaning, right? If you do a top hat filter, then that's just a sharp drop from 1 to 0 at some specific frequency. If you're doing, say, a Gaussian filter, then there's a cutoff. The cutoff is the half width of the Gaussian in Fourier space. So for each of the filters, there's a logical interpretation of where what the cutoff means. But that allows you to say interactively do. Actually, let's do that. Let's go back to filter tool for a minute. We'll run filter tool again, and we'll have the same set of operations we had before. So here we've got filter low pass dot top hat, and if I just change that now to a filter low pass Gauss, I have exactly the same set of parameters that I could pick here. And I'd say, well, what is the difference between these parameters? If I mouse over one of those carefully, processor radius in terms of Nyquist frequency, 0.5. So 0.5 for cutoff ABS corresponds to Nyquist frequency. For a top hat filter, that wouldn't do anything. For a Gaussian filter, if I said 0.5 here, it would still do a little bit of a low pass filter, because that would be the half width of the Gaussian. I could also specify it as a frequency. So this is a cutoff in terms of spatial frequency in 1 over reciprocal angstroms. So here, if I say 0.1, it means 10 angstrom resolution. If I say 0.2, it means 5 angstrom resolution. Sorry, yeah. And then there's cutoff pixels, which is a specifying the pixel, the cutoff in terms of Fourier pixels. So if it's a 64 by 64 image, and you say 32 pixels, that would be Nyquist. But if it's a 128 by 128 image, and you say cutoff pixels, then it would be only a quarter Nyquist. Half Nyquist. Then there's another one which is cutoff resolve, which is a resolvability cutoff. So when you say the half, so if here you say the half width of the Gaussian in Fourier space is at 10 angstroms, that gives you more than 10 angstrom resolvability if you look at the image in real space. And this is a big confusion for a lot of people who are kind of new to the field and image processing in general. If you have information content at the level of 1 over E at the particular spatial frequency, there's still a lot of higher resolution information present there in the image if you're doing, say, a Gaussian low pass filter. So that means that if you put that 1 over E cutoff at 10 angstroms, you still have information that, some information from 5 angstroms present there. And it's enough to actually give you much better resolvability than you think. So when you say cutoff resolve instead, so here, let's do this. Let's say cutoff frequency. So I only want to do one of these at a time. And we'll say 0.1 here. Okay, so that corresponds to a what most people would call a 10 angstrom low pass filter for cryo-EM purposes. Okay, if I now do this instead, and I set this to 0.1, I have to turn off the other one before it'll take effect. Oh, maybe I didn't. Maybe that one. If you have them both turned on, then one of them will dominate over the other one. Did it update? What happened? Failed to create compose? No, I don't think there was an error message there. All right, let me change this to 0.2. Okay, 0.1. Okay, good. Now let's turn that off and cut off frequency. Those two should have been different, but for some reason they're not different. All right, I now have no idea what's going on there. So resolvability, there's a direct mathematical relationship between resolvability and frequency, but they're not supposed to be exactly the same. I don't know why they're showing up as being the same here. All right, I'm gonna have to look at that later. This should be correct. All right, let's see how else we could visualize that. All right, let me instead of doing a 3D volume,
they look very different for me.
Huh? It does look different for you?
Yeah, there's way more high resolution information.
Yeah, okay. So I don't know why that's failing for me. That's kind of weird. I'm going to run this on particles. Yeah, we'll do this. Particles. This is going to be a big stack of particle images. So if you run filter tool on a stack with lots and lots of particles, it will only show you a subset of the stack. I don't remember exactly how many it limits it to, but it limits it to something like 100 or something like that, or 150 roughly. And they're randomly distributed throughout the population. Now, the things we're looking at here, this is a subtomogram averaging data set. So these are actually individual tilts from a single particle that we're probably seeing here. And you can see this particle had a lot of contamination and stuff floating around, but for our purposes, it doesn't matter. So if I turn off the filter here, that's the original particle. Now it's on. Let's set this back to 0.1 and see if it does the same thing here. Okay, so 0.1, cut off frequency. Yeah, for some reason it's not changing for me. All right, let's look at it a different way. I can add it. So you can add additional views. So here we're seeing the tiled 2D view. If I add a single 2D view here, now I can just see one image at a time, right? I can scroll through them. You can see how that's a tilt series. So I can then open the control panel, and I could compute the Fourier transform in real time. Right, so there's the FFT. If I turn off the filter, that's what the Fourier transform of the original image looked like. Now I can turn on the filter, and if I grab my slider here, I can see how the filter changes. So I can see the real-time impact in Fourier space. All right. All right, I think that's all I wanted to do in filter tool again there. So given that there's a lot of these things that you probably can now do in NumPy, why should you use EMAN's routines for doing these things? Well, it depends on the situation. There are some cases where it probably makes reasonable sense to do it in NumPy. So if I were doing a thresholding operation, again, just like Eric asked about before, if I were doing a thresholding operation, I would say you could do it equally well in either NumPy or EMAN2 with the processor. And for me, it would depend on whether I was working with EM data objects or I was working with NumPy objects. if I had a sequence where I was using NumPy objects, I would probably stick to NumPy, and if I had a sequence where I was using EMData objects, I would stick to EMData. So there are cases like that where you could do it either way, and it's going to be equivalent. Just remember, if you change an if you change a NumPy array which is tied to an EMData object, you have to call update on the EMData object to get it to completely, to update the statistics and stuff. Now, let's say you wanted to do something like this, a low-pass filter. So if you wanted to do a low-pass filter with NumPy, how would you go about doing it? Certainly you can. If you look in SciPy, you can probably find image processing operations which will allow you to do low-pass Gaussian filters. However, you're probably going to start running into definition problems. So if you go to SciPy and you do a low-pass Gaussian filter in SciPy and you say, oh, I did a 10 angstrom resolution low-pass filter in SciPy, are you sure you actually did the equivalent of what you mean in cryo-EM when you say I did a 10 angstrom low-pass filter? Are you sure that the threshold value that you used was actually the same? In most cases, the answer will be no, because different image processing fields define things like resolution in somewhat different ways. If you look at, say, optical microscopy, resolution and resolvability are generally used interchangeably, and it's usually defined in terms of the Raleigh criteria, which defines how far apart two peaks can be and you can still resolve them. And in fact, that's the criterion that's supposed to be used when you run the low-pass Gaussian filter and you specify a resolution, the resolution, sorry, the resolvability cutoff for the low-pass filter instead of specifying the cutoff frequency. So cutoff frequency uses the cryo-EM definition of, if you say 10 angstrom low-pass filter, it means cutoff frequency 0.1. If you said cutoff resolve, that should correspond to a Raleigh criterion cutoff of 0.1. It should be more heavily filtered. So there will be a lot of cases where it can actually be dangerous to, from a publication perspective, to switch to SciPy and do some of your processing operations in SciPy unless you really are careful with your mathematical definitions. Now, there are lots of other cases as well where it's probably easier to deal with things in EMAN2 than it is to deal with the things in NumPy. Now, for dealing with real space images and you want to do something like change the value of a pixel right here to some other value, you can do that in EMAN, you can do that in NumPy. The syntax is pretty much the same. It's fine. But let's say you wanted to go into Fourier space and you wanted to write your own filter function in Fourier space or something like that. If I say, D is equal, let's call it F. F is equal to A.do FFT. That will compute the fast Fourier transform of A. So A is now an EMData object which contains Fourier data. If I say E3 display, F image, I'm going to put it in yet another window, test 3, I will see Fourier space. Okay. Now you can already tell the image display widget that you want to look at Fourier space or real space directly, but it will come up by default in Fourier space if the object is already in FFT. Another way I could find that out is here. I could say f dot is complex. It is complex. Or I could say f dot get attribute dictionary, and you'll see that one of the properties of the data object is complex, and it's 1. You'll note there are a couple of other things here, though. One is complex Ri. Another is complex X. So what's going on there? So you can represent your complex images either as real imaginary pairs or as amplitude phase pairs. The default is real imaginary. That's what most FFT routines will return. And it's expensive to convert from real imaginary to amplitude phase because you have to do an arctangent. You have to do trig functions basically to do the conversion. So in EMAN, I can say F, well, let's not do the conversion right now. Let's just talk about the object first. So if it's a complex object, and if it's a real imaginary complex object, now if I have F and I say 5, 5, that's going to give me a complex value located at that point in Fourier space, right? So that's going to go from the origin in Fourier space in the middle there to 5, 5. Okay, that's not how the data is stored in memory. If you look at the actual image data, if you look at the actual data stored in F, F of 0, actually, it's still going to give me complex numbers if I do that. All right, let's say F dot get value at 0. Okay, that's 891. Now, how do I phrase this? All right, when I call get value at and I say 0, 0, that's with respect to the lower left corner of the image data. It's the first pixel value in the image data. If you look at the Fourier transform, the way the Fourier transform is represented, this is actually the middle of the image, right? The origin in Fourier space is in the center. When I say F of 0, 0, like that, it's going to get me the value at the Fourier origin, which does correspond to the real space origin. Where it gets tricky is where I say y is minus 1. Or y is minus 5. Oh, actually, that's... All right, I have to take it back. When you call it this way, with just giving it parameters at the parameters inside square brackets like this, it's apparently giving you pixels at particular locations in the raw image space. If you want to get the pixels in terms of this Fourier origin, you have to say f.get complex at. Let's try that. And now let's try 5 minus 5. There we go. I'm surprised. I could have sworn that did a get complex at. Obviously, I don't use it that way very often. Yeah, apparently that's considered out of bounds for the image. Anyway, so you have this operation get complex at, which will give you pixel value, which will give you values with respect to the Fourier origin and correctly handle wrapping and that sort of thing. Okay, so the organization that the FFT algorithm, irrespective of the package that you use to do your FFTs, if you do your FFTs in NumPy or you do your FFTs in using the FFTW, which is what EMAN uses to do its FFTs, all the libraries basically use the same convention, which is that the Fourier origin goes at 0, 0 in the image, and then it wraps around as you get halfway up the y-axis. And on the x-axis, it has half as many complex values as it does on the y-axis, plus 1. Anyway, the organization of complex images is tricky. If we look at f of nx, we'll see 134, and f of ny, you'll see 132. And if we look at a of nx, you'll see 132. So when you take the FFT of the 132 by 132 square image, what you get out is a 134 by 132 real values, or 134 over 2 by 132 complex values. Okay, and it's organized in such a way that there's redundancies that are present in Fourier space, and you have to be really careful about all of these things. Being careful about all of these things in NumPy is really tricky. If you're doing it in EMAN, you can pick which way you want to look at the image. If you want to look at the image in terms of pixel locations, in terms of pixel coordinates, you can do it this way, or you can say get value at. If you want to do it in terms of Fourier coordinates, where 0, 0 is the middle of Fourier space, and you can specify negative values for x and for y. Okay, so if we say 5, let's do this. Let's say 5, 5, and we get that. And if we say -5, -5, we should see the complex conjugate, which we did. You can see just the sign changed. Okay. So if you want to operate in Fourier space, you can use this get complex at, and you can get access to the entire complex plane. And you can also call set complex at. So I can say get complex at -5, -5. Let's do this. X is equal to, and X is now this, and I can say f dot set complex at -5, -5, and then set the value of 0. Now let's say f dot get complex at 5, 5, and it's 0. Okay, because there's a complex conjugate relationship between opposing points in real space, the Fourier transforms of real valued images.
What is the J indicating?
Oh, J is I. In engineering, the imaginary number is called J rather than I. J is the square root of -1. Engineers call it J for some reason. I think they used I conventionally for something else, I guess. No, I don't know. It's never really made sense why they changed the convention. Okay, that wasn't an extremely rational description of that, how that works, and I didn't explain how numbers are laid out in Fourier space and that sort of thing. But
I was going to ask, would it? And I don't know if it's worth it.
Go ahead.
But just, I know you had that drawing app that you pulled up before. When you're talking about the wrapping, I think I'm understanding, but I don't know if it would be helpful if you like just sketch out what you're saying, or I don't know. Again, you don't have to.
No. I understand your confusion. And like I said, I didn't explain that. I wasn't planning to get into that much depth, so I didn't.
This is helpful though for me.
So, all right. So if you look at the Fourier transform of a 2D image, which is what we're looking at here on the left, I can actually put it in color, right? So now we're seeing amplitudes and phases over here, where the color represents the phase and the brightness represents the amplitude. When you take the Fourier transform of a real valued image, then any value here reflected across the y-axis is going to be exactly the same value over here with a complex conjugate, right? So the value here is exactly the same as the value down here, but with the complex conjugate taken into account. Only the right half of the Fourier transform is actually even stored. So we're presenting this as a symmetric object about 0 in the middle, but in reality, only the right half of this is even stored in memory. It's just rendering the other half from this half.
But I think what I was referring to is when you were talking about how it's corresponding to the real image. That's when the wrapping, I was getting confused with what you were saying.
Oh, you mean how Fourier transform in general?
No.
Or filtering?
When, because you were calling the coordinates of the real, you can call from the Fourier object the real image coordinates, right? Which is what get value at is doing, right? That's what is the
I see. So all right, so when I say get value at, I'm getting the components of the complex numbers are stored in the image as real imaginary pairs. So if I say get value at 0, 0, I'm going to get the real component of the first value. If I say 1, 0, I'm going to get the imaginary component of the first value. And if I say get 2, 0, I'm getting the real component of the second value. So let's take a look at the complex. So we'll say that. Oops, I just wanted to print it. Okay, so you can see this is the same as this.
Gotcha.
And if I said 3, I get this.
That makes sense. Okay, that makes a lot more sense.
Yeah, you're right. I should have explained that better. So this sort of gives you raw access to the floating point values that are stored in the image, and this interprets the access if it's a complex image.
Right.
Okay.
Okay, that makes sense.
Right. So if you want to do any manipulations involving Fourier space, I would suggest you probably are better off trying to do them using EMAN's routines rather than using NumPy's routines, unless you're using a SciPy library or something which is designed to manipulate Fourier values in a more easily rationalizable way. So one of the things which might be confusing, another thing which might be confusing about this is the redundancy. So if you're at exactly x is equal to 0, and you look up along the y-axis here, then based on the reasoning I just gave you a second ago, the values down here should be exactly the same except for a complex conjugate, right? And of course they are, but all of these values have to actually be stored in the image. These values and these values all have to be stored in the image. These values don't because of the complex conjugate relationship. So what that means is at x equals 0, I need to store these values, but I shouldn't need to store these values because it's redundant. There's a similar thing that happens out at Nyquist frequency. So if you look at the maximum frequency over on the x plus edge here, the same thing happens. There's a range of values on this edge, which has to be exactly the same as the values on the edge down here, because of the way Fourier space wraps around. So if you do a Fourier transform, there's two possible results you could get back. So when we did the FFT of our, let's see, where was it? Where were the sizes I was looking at? I must have overwritten them. So A of nx, sorry, nx, A of ny, y is 132 by 132, but the Fourier transform that we got back is B, like that. Oops, sorry, F, like that. It was 134 by 132. So if you call a Fourier transform computation routine, so if you go to NumPy, you'll find there are different versions of the FFT routine that you can call. In EMAN, there's only one that you can call. You can call do FFT, and that's it. There's a do FFT in place, but there's really only one way of calling the Fourier transform. All right. So what I'm trying to say is it is possible to do a Fourier transform in place, meaning that the return object, the object you get back, is also 132 by 132 pixels. But if you do that, what you wind up with is these values are not the same in memory as these values, because it takes the values from here and it puts them down here, the way it returns the data. So data that you think is at x equals 0 when y is negative is not actually x equals 0 data. It's actually x equals Nyquist data instead. And that's because that's where it has space for the data. It doesn't need to use the space for that, so it can use the space for that. So there's a one-to-one relationship between real space and Fourier space. There's no information loss, information gained. If you have 10 variables in real space, it takes exactly 10 variables to represent that information in Fourier space. So when we get this bigger image back, the reason we get it back is because of this redundancy. And the reason the redundancy is put into place in the actual returned image data is to avoid the confusion of having values where you don't expect them to be. So if you call sort of the default FFT algorithm in NumPy, you wind up with this confusing organization where you have to do all sorts of extra math to pull out the values that you want. If you do them with an EM data object, then you'll get back this case where the object is padded by one complex value in the x direction. And if you call get complex at and set complex at, it's always going to do what you expect it to do. It takes care of all the funny rearrangements and stuff for you.
Are you able to, I think I understand, but also this could be where, just my Fourier,
Okay.
understanding is limited. Are you able to just print just the first part? Is there a way to visualize the numbers so that I could just see what you're saying of or I don't know, could you point to the padded on the F array, on the Fourier array, the padded numbers that you've added?
You want to see the raw FFT?
Well, I just want to see where is the pad being added? Is it being added in the beginning, or is it being
I
added
think
in the
probably
end,
Google
maybe
is
I'm
probably the best solution to this.
Maybe I'm not conceptualizing correctly. And if this makes sense to other people, then we can move on. But, I can
image representation. Let's see what we get here. I have a slide somewhere for this myself, but since I don't have it handy, it's probably hang on. Let's not image representation. Image data organization. Actually, it may. I think the Wikipedia page may actually have that. Let's take a look. Maybe do FFT.
Dr. Baldwin said numerical recipes.
Numerical recipes does, but then I'm going to be holding a book up to my camera.
He said there's an online version.
Oh,
but yeah.
There's an online version of numerical recipes? It's free?
He says he thinks so. I'm the Dr. Baldwin.
I'm not going to go looking for it now. Yeah, this is only showing 1D.
It's okay.
All right, I'm not going to do it today. We'd spend too long digging for it. It's I'll show you my copy of numerical recipes after we're done.
Okay.
I still have it because it has a nice picture and it's pretty easy to see.
Okay.
Wow, we've gone for an hour already.
You just get caught up in Fourier.
No, yeah, sure.
Good.
So if you've got, I mentioned, we talked about processor, doing processing and processing in place and that sort of thing. So I mentioned there were all of those other modular classes, and while E2proc2D can be used to do processing with -- process, right? I can say E2, oops, what the heck? I can say E2proc2D.py, A.hdf, B.hdf, -- process, filter.low pass, etc. Some of those other classes, that wouldn't make any sense. There's no comparison mechanism. So if I want to compare two images, so I've got A and B here. A and B are the same size. Let's actually display. All right, we'll do this. E3 display A, B, image MX. Why didn't I get a response? Didn't like something. It has to be a list. Oh, All right, it didn't like it that was a tuple for some reason. Okay, so there are two different images. Let's say I want to just compare those without aligning them. I can say a.cmp and then a.cmpb. I think I may have that backwards. Yeah, sorry, it's the other way. There. So that's the negative of the cross correlation between those two images. That'd be the equivalent of a dot product. And you'd say, well, why don't you just use NumPy and say a dot b instead? And the answer is, well, what if I want to compute a Fourier ring correlation? I can just say FRC here, and then I can get the Fourier ring correlation, which is the same. That's bizarre. Well, that's hard to believe. Yeah, FRC is right. All right. There are optional parameters like amp weight. Oops, sorry, dictionary. So it's formatted just like a processor. Yeah, all right, there. So the way you call this is just like calling a processor, where there are parameters that you can provide. If you don't provide any parameters, then it'll use default values for everything. And if you try to do something like CCC, which doesn't take amp weight as a parameter, then it'll yell at you because it doesn't know what that parameter means. But it does mean that any place where you want to compare A and B, if you do it using this comparison operation like that, you can swap out the algorithm really easily for a different algorithm without having to modify your code. So that concept is also used throughout EMAN command line programs a lot, and is also very useful at the Python level. So the different types of classes will have different methods associated with them. So for comparison, it's a.cmp b like that. If you want to align something, it would be a.align translational to b, and then that would return a new EM data object. Let's do that. C equals, and then we can do this and look at C2. Oh, it updated here. Oh, there it is. And now C is better aligned in theory to A, B, and C. Now, since I only did a translational alignment, it didn't do very much. So let's try rotate, translate, just with default options. And display it again, and oh, look, now they're in the correct orientation with respect to one another. So for each of the different modular classes, there are corresponding methods in the EM data class to deal with the operations, basically. Probably the only real exception to that would be the like the averagers or the reconstructors. If you want to do something with an averager, you have to create an averager object and then add images to it. I can do that really quick. Let's say avg is equal to averagers.get mean. And then I can say avg.add image A, avg.add image B, and then x is equal to avg.finish. So I'm going to put this all in one block, like that. And then let's E3 display X image. Okay, so that's the average of A and B. I could do the average of C and B, and it should look a lot cleaner because they were in the correct orientation now. But we can go back to A and B, and you can see it. Now you'd say, well, why did I bother doing that? Why didn't I just say A plus B or something like that? Because I'm just taking an average. Well, again, the difference is there are different sorts of averagers available. E2 help.py averager, and you can see that there's mean, but there's also a median or a min-max. So if I don't want to get the mean value, if I want to get the min-max, like that. Now you can see I've got the minimum value in each pixel location from the set of images that I provided. If I want the maximum instead of the minimum, you can see one of the arguments is max, which is a flag. So then when I get it, I would say max, which defaults to false, true, or 1 being true. And now we get the maximum value out. So it basically gives you a lot of flexibility. So if you use this style of programming in EMAN2 with EM data objects, it allows you to very quickly alter what you're doing in interesting ways. So, you know, say you do the mean, and then, oops, sorry, it doesn't take that argument, obvious, that parameter. So I say I'm doing the mean, and I say, well, what does the median look like? And the answer is, in this case, pretty similar. But if we looked at specific pixel values, it would probably be a little different. Oh, let's do that. Let's say, all right, we'll go ahead and do this. And then we're going to do it again, but we're going to call it y, and we're going to call this mean. And now I've got an x, which is the median, and y is the mean, and I can say z is equal to x minus y, and E3 display z. And, well, really got almost nothing there. Hang on, let's open it up here. Image test. Full contrast. Oh, mean 0, max 0. Huh, why? Is it really? They were exactly the same? That's hard to believe. That can't be the case. Why? Oh, sorry.
Where did you call X?
No. All right, no. So I gave you a bad example. So what's going on here? Why did the mean come out to be exactly the same as the median? The answer is the median is an undefined operation if you have an even number of images, right? If you have 3 images, then you take the middle value. But if you have only 2 images, well, then you take the first or the second. So in the case of a median with an even number of values, you usually take the average of the middle 2. Mm-hmm. So since I only had 2, it was taking the average, which is exactly what the mean was doing. So there actually was no difference between them. Now, if I average together 3, I'll go ahead and do it real quick before we finish up. So let's go ahead and we'll do A, B, and C, C being the aligned version of A. And we'll do that with Y. And then we'll do median and set it to X. And hopefully now we'll see a difference. Oh, good. All right, I'm not going crazy. So there is actually a difference between the median and the mean. So
heard it here.
Huh?
Sorry. I said you heard it here.
Yeah. So anyway, you can see the sort of flexibility that you can get out of doing this sort of thing. Again, E2 help.py gives you a list of the different types of things. You know, so we looked at processors, and we looked at comparators, and we looked at aligners, and we looked at averagers. There's also making projections and reconstructions, and analyzers, which can do things like do k-mean segmentation and stuff like that. Yeah, anyway. Okay, that's probably enough for today. Anyone have any questions?
What segmentation? K-mean?
K-mean, sorry,
Oh.
K-means segmentation.
K-means. I think you said
Yeah,
K-means. I was like, what?
no, sorry. Yeah, for clustering. So,
Right.
so segmentation is something that you can do in different contexts. You can treat the process of k-means segmentation differently in different contexts. So you could treat it as segmenting out clusters of objects in space, but you can also do it on pixel values.
Gotcha.
So if you look at the list of analyzers, you'll see that there's a k-means, and you can do principal component analysis with analyzers. You can do Verimax. I thought we also had a watershed segmentation algorithm in there, but I don't see it. I wonder where that is. Huh. Oh, maybe the watershed is actually a processor, because I think that's that the way it's being used there, I think it can be treated as a processor instead. So e2 help.py processor segment. Yeah, there we go. So so there are processors which do k-means, watershed, subunit. So these are different types of segmentation operations, which are actually image processing operations. This k-means segmentation produces discrete clusters of things as outputs. So different purpose. Okay. Any other questions?
I was wondering if you had any like books or learning material you would recommend for learning more about image processing.
In general, or
Yeah,
specifically for cryo-EM?
Well, if there is one specifically for cryo-EM, but I kind of doubt that.
Oh, there is. No, so back in like 2000 or 1998 or a long time ago, Joachim Frank wrote a book on cryo-EM image processing, and he revised it sometime in sort of the mid 2000s. It's pre-Relion, but other than that, the maximum likelihood stuff was actually first done in cryo-EM by Fred Sigworth back in the late 90s. So I think there actually are some references to it in there. I wonder if I've got it on my shelf here.
I've watched a number of Sigworth's YouTube videos and found them to be pretty helpful, if a little bit confusing at times, but I've not found any books that.
Yeah, this is the book in question. Three-dimensional electron microscopy of macromolecular assemblies by Joachim Frank, and it's an image processing book much more than a cryo-EM book. So yeah, I mean, I'm not going to show it. I'll hold it up to the monitor, but it's an excellent reference for learning general cryo-EM image processing stuff.